Hi guys, so I'm going to start the unit about simple harmonic motion and I'm going to start easy. So I will go through the fundamentals and it's just going to be algebra based physics. So just very simple stuff you need to know to solve, for example, MCAT questions. And then I will go more into calculus. I will do some calculus later on. But let's start simple. So each time you have an object that is elastic, then it can oscillate. If you can have the restoring force, like we have seen just before, the restoring force, which is proportional to the displacement from equilibrium. So it means if you have a strain proportional to the stress, so then when the object oscillates, will start to oscillate, then you can have a simple harmonic motion. It does not have to be the case, but any oscillation, most of the time, you can, to a good approximation, um, think of it as a simple harmonic oscillator. Okay, so simple harmonic motion or simple harmonic oscillations only happens when we can say to a good approximation that the restoring force, so restoring force is the force that wants to bring back the object to its initial shape, is proportional to the displacement. Now, restoring force means acceleration. Okay, so if you think of that object only being acted upon by the restoring force, right? So you have the force here, F net equals the mass. Let's say that could be the mass, the mass of a load on a spring equals acceleration. You see that the net force is always proportional to the acceleration. So if you have the restoring force, which is proportional to your small displacement about the equilibrium, so then that means the acceleration is also proportional to the small displacement about the equilibrium. So remember from Newton's second law, if you have, for example, a net force here, so if this is the net force here, then depending on the mass, but the acceleration will have exactly the same direction. So maybe you're going to have an acceleration with that magnitude here, if the mass equals 3 kilogram and it's acted upon by a force here, then the acceleration will be the force divided by 3. Of course, you can have the opposite. That means you can have acceleration here, and that will be the net force if the mass is smaller than 1. Okay, so the mass is, for example, 1/3. So then, of course, the acceleration will have 3 times the magnitude. But that's the idea. So a lot of things can be thought as able to provide those harmonic oscillations. So you can have a pendulum. If the angle is small enough, that's going to be simple harmonic motion. Tuning fork, it's going to oscillate. It's going to be a sound wave. It will be also a simple harmonic oscillator, maybe gravitational wave produced by 2 black holes, for example. Maybe you can approximate that with a simple model. You have here a swing. So you see all those oscillators, they like to swing at their own frequency, natural frequency. Okay, it's used a lot in engineering. Like, for example, you have a machine, maybe the machine is going to vibrate at its natural frequency. So then if you want to describe what's going on here, you can use a simple oscillator. Maybe that's going to be your machine. That's going to be the spring. You can find K such as it will vibrate here at the same frequency than the machine that you have here. Okay, so let's go back to my sim. So here you have a mass here, 100 grams, and I have no gravity to make it simple to begin with. And I'm going to show you the spring constant here. There is no gravity. So I'm going to pull on it, right? So because I'm pulling on it, you see in blue, that's going to be the restoring force. So here, the restoring force is maximum. When it's at equilibrium here, you have no restoring force. And then if I compress here, again, you're going to have a restoring force. So the restoring force is proportional to the displacement relative to the equilibrium. So I'm going to pull here. That's going to be called the amplitude. And there is no friction, no air resistance. And you're going to see it's going to oscillate about its position of equilibrium. So you see the force here, it's going to be large, then it goes to 0, then it's going to be large again. Okay, so if you look at the sign here, it's going to be negative, 0, and then it's going to be positive again. Now, if you look at the acceleration, we see that the acceleration has exactly the same direction, just larger because the mass is small, 0.1. So 0.1 means it's divided by 10, but you get the idea. So acceleration is maximum, acceleration is 0, acceleration increases again with maximum, goes to 0, and so forth and so on. So each time you have the restoring force, then you're going to have the acceleration. And they are both proportional to the stretch. Okay? So now you might ask, how come when it's going through its position, how come it doesn't stop? That's because of Newton's first law. An object in motion wants to stay in motion in the same direction at the same speed unless, acted by an opposite force, but it will take time to stop it, right? So here, there is no force. So because of its inertia, it wants to keep going in the same direction at the same speed, except because there is a restoring force here, it's gonna slow down, stop, speed up, slow down, stop, speed up, slow down, stop, speed up, slow down, stop. Okay, and so forth and so on. If you look at the velocity, that's going to be in green. You see that the velocity is 0 here, maximum 0, maximum 0. So you see how it goes from 0, 0, maximum again, 0, maximum again, right? So that's going to be for the velocity. So just for you to get an idea how it works. So by the way, what's going to happen when the spring is stretched out or when it's compressed, it's going to have potential elastic energy. So here it's all elastic energy, and here it's all kinetic energy, potential energy, kinetic energy, potential energy, kinetic energy, and so forth and so on. So we're going to see that later on. So the main idea is that here we're going to get a simple harmonic oscillation with the acceleration proportional to the displacement. So, for example, if I stop here, that will be the displacement here from its equilibrium, and that acceleration here is proportional to that displacement because the restoring force is proportional to the displacement. So you see here, it's a motion that repeats itself. Okay, so this is called from here to there, this is called the amplitude. From there, I don't know where it was. So here it's the amplitude from here to there. And what else? Okay, so one cycle, it's going from up and then down and then back to the same position. So that's one cycle. The time for one cycle is called the period. So let's find out what kind of relationship you have between the period. So the period, it's going to be T. Unit is in seconds. That's going to be the time for one cycle. So for example, you have your spring here. You stretch it. So we don't worry about gravity for now. So you stretch it here. That will be the amplitude of the motion. So it's going to go from here. It's going to go past the equilibrium and then from back here. The time it takes to go back here to the same position, that's what we call the period. So let's see. Let's compute the period in that case here. Yeah, let's make it here. So I have a timer. So I'm gonna, because it's very slow. That's the normal motion, you know. So if you do that in a lab, and the next video, I will show you a lab that we did in class. But what is nice with the simulation, I can make it go slow. If you are doing a lab, usually we go for 10 oscillations. But now, because it's slow, we're going to go for 4 oscillations. So I'm going to start when it's here, right? Let's see. Starts. So that's half of oscillation. That's 1 oscillation. 2 oscillation. 3 oscillation. And 4 oscillation. So 3.24. So the period, I get the period is 3.24 seconds for 4 oscillations. So 4 oscillation is 3.24 seconds. So the period, that means the time for 1 oscillation is going to be 3.24 divided by 4, and you get about 0.8 seconds, right? Okay, so that's to find the period. Now let's see what's going to happen if now I increase the amplitude. So it means I'm going to increase the amplitude here. Let's see if it's going to have any effect on the period. So I'm going to start over. I'm going to count for 4 oscillations. So I start here. That's going to be half. That's going to be 1. 2. 3. 4. Boom. 3.24. So what does it mean? It means that the period does not depend on the amplitude. Okay, so it means I can make a very small amplitude. You can do that on your own. I can make it a very small amplitude here, and it's going to take still 3.24, right? So we start from here. 1, 2, 3, and 4. It's going to be about the same. It's just that I didn't start at the right moment, but the idea, it does not depend on the amplitude. So that could be conceptual question, right? On the MCAT, for example. So what's going to happen if I increase the mass? So now I put 250. I forgot where I was, maybe at 20. So that's going to be my amplitude, but the amplitude doesn't matter, but the mass here, so that means more inertia. So you're going to apply the same restoring force, because restoring force does not depend on the load. Restoring force depends on the displacement here. So I'm applying for the same restoring force here, have the same restoring force here, the same displacement. What's going to happen to the period? But now you have more inertia. So you should get a longer period, isn't it? So let's see. So it's take forever. Start here. That's going to be 1. That's going to be 2. That's going to be 3. You see, we are over 3.24, and that's going to be 4 cycles. So about 5, right? So now we have that 4 cycle will take about 5 seconds something. So the period increases when the mass increases, right? So what about the spring constant? So I take back my mass here. So remember the period was 3.24. What's going to happen if I make a large spring constant? So either I increase the density here, or I change the material, or I can take a shorter spring. Okay, so what's going to happen to the period? You can pause the video and think about it, or you can do it on your own. You see, obviously, it's going to go much faster. Okay, I don't know if you want me to do the computation, but you see, it goes 1, 2, 3, 4. Boom. So the period now is 2.30 seconds for 4 oscillations. So it means that now we have 40 is about 2.3 seconds. So before it was 3.24. So now it's much less, meaning if the spring constant increases, the period is going to decrease. And I will show you why in the coming video, but the period of a simple harmonic motion, when it's a spring, it's going to be equal to 2 pi, and then you have the square root here, and then it's going to be here at the top. You can guess it's going to be the mass, of course, because if the mass increase, then the period is going to increase, and here you have your K, the spring constant. The mass is in kilogram, K is in Newton per meters, and the period is in second. What we call the frequency is actually the number of cycle per second, and the period is the number of seconds per cycle. So you can see that the frequency is just 1 over the period. The unit is hertz, or that will be the notation, but it means the number of cycles per second. So if you go back to here, so if I can count how many cycles do I have in 1 second, that's going to be the frequency. So I can do in 1 second. So I have to go back to do 1 cycle. Stop. Okay, so it's in that case, you have 1 cycle per second. That will be about 1 hertz. Okay, if it's moving faster, then of course the frequency will be larger. Except here it's slow, but you can forget about that. So anyway, what else? So in the lab, I'm gonna have I will show you a lab in the next video. But what you can do, you can try. So what you can do here, if you square on both sides, you're gonna see that the period square equals 4 pi square over k times the mass. So if you increase the mass, the period increases. So this is a nicer relationship because now it's like y equals mx, and that's going to be the slope. Okay, so it means if you do an experiment, here you have your t square, here you have your mass, okay, and you should have a line. So you do the experiment with the same spring, different mass, and you find, for example, how long it takes for 10 cycles, and then you divide by 10 to find the period. Then you make your graph here. So period square versus mass. Now the slope here, which is rise over run, it's going to be equals to 4 pi square over k. Okay? So you can find k. That's one way you can use that relationship. It's a linear relationship. Or if you have an unknown mass, and you find the period, then you can find the unknown mass. So that's what it is done in, for example, in the space station here. You cannot step on a scale, obviously, because everyone is in weightlessness. I mean, everything is floating inside. So what they have to do is secure themselves on a spring like this. So that will be the astronaut plus the chair, and they will vibrate, and finding the period will give the mass of the astronaut. Okay? You have another setup here, but the same idea using this equation there. Okay, so we can do an example here. Okay, so let's try to do this one. So you can pause the video. So that example come from a book, Johnson and Cutnell, Physics. by Johnson and Cutnell. And it's a very nice book if you are working for the MCAT. So here you have the model. Here you have a spring with a spring constant. And here you have your load. So that will be the mass. That mass here will be the mass of the astronaut plus the mass of the chair. Then move a little bit here, push it down, and it's going to vibrate, and you find the period. And the goal is to find the mass of the astronaut. So you can use that equation here, T equals 2 pi square root of, and then you have the total mass here divided by K. So you square both sides. So that's going to be 4 pi square times the total mass divided by K. Then you can plug it in. So the period is 2.41 square equals 4 pi square times the total mass divided by the spring constant is 606. And then you can isolate the mass. So it's going to be 2.41 square times 606. And then you divide by 4 pi square. So that will be the total mass, including the chair. So I don't know how much I found, like about 89 kilogram. So that's going to be the chair plus the person. So the chair is 12 kilogram. So the mass of the person will be 89 minus 12, and you get 77 kilogram. Okay? So one thing that you use, you also find in the problems is, and I will get back to that, but just quickly talking about elastic potential energy. So it's potential energy. That means storing energy. So if I have my rubber band here, my Pilates band, if I stretch it here, I'm doing work on it. I'm applying a force over a distance, and all the energy I'm going to put in that system is going to go into the band being stretched, right? So that's going to be potential energy. It's being stored, and that energy can be recovered. If I let go, I can even hurt someone, right? So you have potential energy stored inside that spring, and then you can release that energy. So the equation for the potential energy is 1/2 K, that will be a spring constant, and the stretch square. So it means by how much it was stretched here. So 1/2 K x squared. So this is unstrained. That will be your delta x. So delta x squared. That's what you're gonna have in your potential energy. Okay. So I will go back to that. It's just to be able to do some of the problem here. So the first problem is a typical AP question or MCAT question. It's an easy one. It talks about heart. So it's not a harmonic oscillator. The heart is not a harmonic oscillator, but we can still find the period, right? So the heart beats here, beep, 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 beep. So the period will be that time here between two beats. So that means that, I don't know what's the question actually. 150 beats per minute. So you have 150 beats for 1 minute. So 1 minute is 60 seconds. And they want to know the period. So it means the time per bit for 1 bit. So that means here you have 1 bit is question mark. Okay, so that means the period is going to be 60 divided by 150. So it's going to be about 0.4 seconds. Of course, it depends if you are exercising or just being relaxed. But you see here, it's kind of makes sense here. That's 1, that's 2. So that's 1 second. That's about 0.5 seconds. Half of a second. Okay? So one thing I didn't explain here is that if you do have gravity, so I have gravity here. I have gravity. Everything is falling now. And I go back to the same setup. I think it was this one. So I have gravity here now. Okay. So that's a natural spring, but gravity is here. It doesn't matter that you have gravity. You're going to see that the period, and I will explain why. But even if you have gravity, so here it's in equilibrium. It's in equilibrium between the spring constant and gravity, right? So here it's in equilibrium. You have mg pulling down, and here you're going to have a spring constant pulling up. But that's not going to affect the period. So, matter of fact, if I move now to here, you're going to see you're going to get exactly the same period. Start here, 1, and then 2, and then 3, and then 4, so you see it's about 3.20 seconds like before, except I don't have a good reaction time. My point is gravity does not influence the period. And I will explain why. But it doesn't matter if you have gravity or not when you have a vertical spring. Okay, so let's go to the next question. So you can pause the video and try to do it on your own. No, that's not what I want to do here. So the first thing you want to do is draw the situation always. So now you have a vertical spring, okay? So now it's at rest and it's happy. And then now you have a mass. So because you have a mass here, now it's going to move here. So that's going to be a mass here. It's not oscillating yet. It's in equilibrium and it has been moved here to here, right? So that's, you have a little stretch here. Let's call that G. So it's in equilibrium between the weight here, which is mg, and the restoring force here, which is k times the displacement. So that's just Hooke's law, right? So you can say that k times the small displacement equals the weight. So you have 1, 1, 1, The small displacement here is 0.340. So this is 0.340 meters or 34 centimeter. So 0.340 equals the mass times G. We're going to say it's 10 to simplify. So that's going to give you the mass. So the mass is that times this divided by 10. We can do it. So double check what I'm doing. And you get 3.77 kilogram about. Okay. So that will be answering the first question. Okay. So now I take the same one. So from here, so it's already pulled by 0.34 centimeter. And then I'm going to pull even more. So still have the same mass here. Now that distance here is 9 centimeter. Okay, that's what it says here. So 0.09. And I'm going to call that delta L. So if you think, and then it start to oscillate. Okay, so that's going to be my amplitude. So it's going to go, you're going to have the force here acting here. You're going to have the restoring force here. And of course, you're going to have the weight here. mg, and it's going to accelerate in this direction. But if you look at the net force here, so the net force here, it's going to be the weight, K, minus K, and the stretch, it's going to be D, plus that delta L here, that will be the 9 centimeter, that's going to be equals to MA. So the net force, there is a net force, so there will be an acceleration. But if I distribute here, you're going to have minus K D minus K delta L equals MA. So that goes away because they are equal to each other. So at the end, the idea is that gravity does not matter. What matters is by how much you pull here, the amplitude here of the motion, how much you pull from this position. And the period will be equals to 2 pi the mass divided by k. So it doesn't even depend on the amplitude. Okay, but the motion is about this position here, right? So it's going to be 9 centimeters and then 9 centimeters. So it's going to oscillate about here. So as far as the motion is concerned, you can forget about gravity. Everything happens like there is no gravity here. Okay. So what do they want? They want just the period. So the period, it's going to be 2 pi, the mass, which is 3.77 divided by k, so 111. So the period is 1/16 seconds about. Okay, so here we have seen that when you have a vertical spring, and so you have a mass, so that's going to be called the equilibrium position. And if it's not moving, then of course it's going to be in equilibrium between gravity, mg, pulling down, and the restoring force pulling up, because the spring here is being stretched relative to its initial position. So you can use that to find the spring constant. So that means K times that displacement here equals mg. So once you have the spring constant, okay, So then you can forget about gravity, because what matters will be the net force, because the net force is proportional to the acceleration. So here I'm going to show you the net force. You see, I'm going to pull that down, and you see that the net force is up, and it's going to be maximum. Here the net force is 0, okay? And then it's going to increase again. It's going to be maximum when the spring is compressed. It's going to be 0, and it's going to be maximum when it's going to be stretched, okay? And in yellow, you have the acceleration. So acceleration is max, acceleration is 0, acceleration is max, acceleration is 0, and then it's max again. So net force, acceleration, that's what matters. And you see that the mass is oscillating about that equilibrium position. So it means it does not matter anymore where was its initial land. Okay? So that's the idea. You can look at the velocity vector as well. You see that it's going to increase the speed. Here it's 0. The speed increases. Here at the top it's going to be 0. So it's, I think it's important to play with the simulation to really understand, because for MCAT, for example, you're going to have a lot of, you have conceptual questions. So if we look at the energy situation, so here you have energies, you have kinetic energy, potential energy for gravity, gravitational potential energy, you have elastic potential energy, so that will be the energy you store in the spring, and that's the energy that you lose to friction or to air resistance, but we're going to neglect that. That's going to be the total energy. So if there is no friction, okay, if there is no resistance, or if we can neglect a resistance, then the total amount of energy is going to be conserved, is going to be the same. So when I put a mass here, as I pull on the mass here, you see that most of the energy is going to be in the spring. So it's going to be here. Okay, so that means here there is no gravitational energy. All the energy is going to be elastic. Okay, you see that on the left. And you see the energy is going to swing back and forth between the three forms of energy. So that's going to be potential here. When the velocity is going to be maximum, it means I'm going to have a lot of kinetic energy. See, kinetic energy is 0, it's going to increase, and then it gets to 0 again. Gravitational energy depends where you put your 0. I don't know if I cannot move that. But if you remove gravity again, so let's say you remove gravity, so you see that the energy is only swinging back and forth between kinetic and elastic potential energy. It's compressed, it's going to be elastic. Here, at the equilibrium here, when it goes through equilibrium, it's going to be all kinetic, then elastic, kinetic, elastic, kinetic, elastic. So it's going to swing back and forth, but the total amount of energy is going to stay the same. Okay? So let's look back at more problems here. Okay, let's do one easy one. Number 6 is easy. Where am I? So we have a spring at its natural frequency. So it means if you let it swing, if you are not driving the oscillation, like here, it has a given period. So the number of oscillations per second is going to be the frequency. We call that the natural frequency. Any elastic object that oscillates has its own natural frequency. So the period is given. So that's going to be the period T. And you have the mass here. The mass is 0.015 kilogram. And they're asking you to find the spring constant. So you see, this one is easy because we have the period equals 2 pi and then the square root of the mass. So remember, as the mass increases, inertia increases. So the period increases because it takes longer. Okay, it takes its time. So that's how you can remember that m here is at the numerator, and that's going to be k. So you can square on both sides. It's going to be 4 pi squared times the mass, and then k. So they want to find the spring constant here. So you see k equals, you cross multiply, so 4 pi squared times the mass divided by the period squared. So I don't know if I have solved this. So the mass is, the period is 0.5 squared. So k equals 4 pi squared times the mass, 0.015 over 0.5 squared. So k is, I think it's 2.4 Newton per meter. So that's a easy application. So let's go for another easy one. These are problems from AP exams. So this one is also easy. You can, of course, you should stop the video, try to do them. So it happens on the road here, on the highway. Oh, that must be in America. We have a lot of that. In the US, we have terrible pavement. So it goes boom, boom. Right? And it's, the crevice here is 2 centimeters. So 0.02 meters. So imagine the car is going to go boom, 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 right? And so 2 centimeters, that will be the distance here. But we want to find out the frequency. So first of all, how long it's going to take to go from that crevice here to this one? And you know that the speed is 30 meters in 1 second. Okay. So if you have 0.02 meters, it's going to take how many seconds? It's going to take 6.7 seconds. So that's going to be the period. So the frequency is 1 over the period. So it's going to be the number of cycles per second. So it's going to be 1 over 0.15, 1 over, so it's going to be 1 over 6.7, and it's going to be about 0.15 hertz. So that will be cycles per second. And luckily you have good suspension here, because sometimes in the old car, in the old way, you used to have spring here. And if you hit the natural frequency, then the car will oscillate like crazy, which is not very comfortable. Okay, so let's see. So this one is a little bit harder. So it's someone climbing here. So you can think of that rope here is like a spring. So the person here is in equilibrium between, of course, the restoring force here and the weight. And the rope has some elasticity. So, for example, if he climbs there, so the rope is not stretched, and if he let go, of course, it's going to be in free fall, and he's going to start maybe to oscillate about its equilibrium, right? In terms of energy, let's say here the rope does not, is not straight, not stretched. He's going to fall here. So it's going to have potential energy here. And then everything will go in the elastic potential energy. But that's the idea. I forgot the question. Okay, so let's try to see how we can solve that. It's very much like a spring, a vertical spring. So the first question is easy. So it's on the mountain here. And then so here that will be the mass. That's going to be the rope here. It's nylon, right? So if it's in equilibrium, there will be the weight pulling down. And of course, the spring constant, the spring force, the restoring force pulling up. So we suppose that he's going to start to oscillate about this position, right? So it's going to go up and then down and then up and down. So it behaves like a vertical spring here, and it's oscillating about its equilibrium position. So the spring constant here is very large. Okay, so it's good. That means it cannot oscillate too fast. That's going to decrease the period. Okay, because that doesn't seem very safe if you go up and down very quickly. So that's going to be Newton per meter. And then the mass here, M equals 90 kilogram. So the period about that position here, again, is given by the equation 2 pi square root of the mass divided by K. And because we want the period, yes, we don't need to square both sides. So that's going to be 2 pi square root of 90. And then you have a big number, which is good. You don't want to oscillate. That doesn't seem very safe. 10 to the 4 here. So that's going to be 0.5 second. So it's going to be 0.5 seconds to go down and then up again. So the frequency is going to be 2 hertz. Okay. And then we have to use, so what's happening here? So what's happening here? He's going to be in free fall. The spring is going to be all stretched. And then all that energy from potential energy is going to be in the, so here I have a cute app. So no air resistance. So you see here it's a bungee jump, but he's attached here to a rope. And when the rope is slacking, so there is no elastic potential energy. There is only gravitational potential energy. So it depends where you put your zero. Let's say you put your zero somewhere there. So here it has only gravitational potential energy. And then at that point here, so it's gravitational potential energy going into kinetic energy. So that amount of gravitational potential energy that you are missing, it's going to turn into kinetic energy. There is no elastic potential energy because you see the rope here didn't start stretching. And then we get to that point here. You see the rope is about to stretch, right? So it's not yet elastic potential energy, but the rope is about to stretch. When you reach the equilibrium position here, so that means mg down will be equals to the restoring force. At that point here, kinetic energy is maximum, right? It still have some gravitational energy relative to the level 0, which is about here, and it starts to have elastic potential energy. Then it's going to be stretched out all the way. Luckily, it doesn't break. At that position here, it has no gravitational potential energy. It has no kinetic energy, but everything is in the elastic potential energy. So that's going to be the question, the part B of the question or the problem we were looking at. So it means if you are in free fall between here and there, so that will be free fall 2 meters, right? All that potential energy is going to be converted into stretching the rope from here to there. So all the potential energy you begin with, okay, is going to turn into gravitational potential energy here. You see, if you go back to the beginning here, everything is in potential energy. Then he is in free fall until there, until that position here. And at the very end, everything is in elastic potential energy. So between the beginning and the end, you see that all the potential energy the person had to begin with is going to turn into elastic potential energy. Okay? And that begins when here, it's about here. Let's start again. So that will be all potential, some kinetic, some kinetic, some kinetic increases. Up, you see kinetic is maximum. Elastic potential energy is about to come in play. Then elastic potential energy increases, kinetic energy decreases, right? So you can take the time and look what's going on here. Of course, it's going to be very quick. So let's go back to the equation, and it's a challenging question, but it was an AP question. So here we found the frequency when that person here is oscillating about its equilibrium position. But the next question is between here and there, you have 2 meters. And let's say at that position here, potential energy gravitational equals 0. So we take the 0 here, and all the energy here is potential elastic energy. Between here and there, the cord is slacking, okay? So it doesn't stretch. Only here it's going to start to stretch. So the idea is that here you have potential energy, gravitational potential energy is max. The potential energy, elastic potential energy is 0. Kinetic energy equals 0. Okay, at that position here, elastic is still 0, and you have some kinetic and some gravitational potential energy. And then all that potential energy is going to turn into potential elastic energy. And the maximum stretch here, let's say it's going to be delta L. So if you look at the potential energy, the conservation of energy, so energy before equals energy after, right? So it's conservation of energy. So before it has potential gravitational energy, and the potential energy is 0. So you're gonna have mg, and the height here, it's gonna be delta L plus 2. At the end, here it's gonna be all in gravitational, in the elastic potential energy. So it's gonna be 1/2 K delta L square. Yes, this is right. And you can really understand what's going on again with the simulation I show you. Okay. So at that point here, physics stops. Okay. That's just math. And you see, it's a quadratic equation that you can solve with your TI. Okay. So the mass here was 90. So 90 times 10. That's going to be your delta L. I'm going to call it X plus 2 equals 1/2 K. So that's going to be 7, I think it's 7,000. So that's going to be 7,000 half of K times X square. And yes, because there is 1/2 14,000. Guess you can try to simplify a little bit, so I can cross this out. So you're going to have, you distribute, so you're going to be 9x. You'll have a 9x, yes, plus 18 equals, is that a 70? So that's going to be 70x squared. So you need to find, you have to solve for x. So that's going to be 70x squared minus 9x minus 18 equals 0. So usually you are given multiple choices, so you can plug each choice in that equation to see which one make that work, or you can use your TI. So here I used Wolfram alpha and to solve that equation here, and I found like almost 0.6. Yes, about 0.6 meters, 0.57. So it's not on scale. The delta L in that case will be here. So delta L should be here. This is 2 meters. Okay, that makes sense because we are not talking about bungee hop. We are talking about someone climbing. So you don't want to have a jumping rope here in that case. Okay? So I hope it was clear. It's a little bit challenging, but again, this is a great simulation to understand what's going on. So I'm just gonna run it. If you are done with it, you can stop the video just for the fun. I'm gonna run it again. energy. Okay, slow motion. So here everything is in gravitational potential energy. The spring is not stretched. And then here it's gravitational energy, kinetic energy, no elastic potential energy because the rope is not stretched. And then at that very point here, the rope is going to start stretching. So some of the energy here, it's going to go into elastic potential energy. Kinetic energy here is maximum, and then it's going to start to decrease. So at that point here, this is the equilibrium position, right? So the mass is going to oscillate about that position here. So kinetic energy is still decreasing, gravitational potential is still decreasing, and elastic potential energy is going to increase until you get here. Oh, I missed it. So here you have potential, kinetic. Kinetic is maximum, elastic potential increases, and stop. Oh, I missed it again. So again, that's potential, kinetic is maximum, kinetic decreases, stop. So here you have no kinetic energy, you have no gravitational energy, everything is in the elastic potential energy. So you have that here, gravitational potential energy, okay, all that gravitational potential energy, it's going to be turned into gravitational, elastic potential energy. Okay, so the next question is very much like the previous one. It's not very interesting and it's a bit challenging. You can try on your own. It's that one here. It's called the bathroom dance. So the idea is that you are excited, maybe you have lost some weight, so you jump on your bathroom scale, the spring inside is squeezed, so all that energy is going to go into elastic potential energy, and that energy is going to be released and go into potential elastic energy. So it's a bit again, you're going to have a quadratic equation to solve. But the idea is that you have your bathroom scale here. Okay, it's minding its own business. It's not stretched. It's calibrated. So there is 0 here. You are reading 0 kilogram and you are all excited and you jump on the scale. So the spring is all squeezed here. Okay, so it's squeezed by amount of delta L. And that's you here. You have a mass here, M. So all that energy here is being stored into the spring here. And we can also say that here has a potential energy, gravitational potential equals to 0. And the potential elastic energy is going to be max. So here the energy total is going to be equals to only the potential elastic energy, because of course it's not moving, so you do not have kinetic energy, so it's going to be 1/2 K and then delta L squared. So that's the amount by which the spring here is being squeezed down. Okay, so you jump and then of course you're going to bounce back. So the spring is going to go back to here, to that level here where it was before, but you keep going here. So now you are at that height here. The height here, h is given, I think it's equals to 2 centimeters. So you have to convert that to meters. And that's your delta L. So the total energy here, it's only equals to the gravitational potential energy, because the spring is not stretched. It's not squeezed anymore, right? So the total energy here, total is going to be M, your mass, times G. So the mass times G times the height above level 0. So potential energy here, gravitational equals 0 here. So it's going to be the delta L plus H. So you have the total potential elastic energy before. All that energy is going to go into the gravitational potential energy. So it's like before, right? It's very much like the that problem here. And again, physics stops here and math takes over, because you just have to plug the numbers. You can solve for delta L. And once you have delta L, so then you can find the potential elastic energy. So usually you have multiple choices, so it's easier, because then you can plug back the numbers to see which one will make that equality right. So I'm going to stop here because I'm running out of battery. But next time we'll talk about pendulum, and we will keep the calculus for later. Oh, and I'm going to post a lab, a demo.